Yeah, thanks for coming. This is going to work with Robert Stewart and Phil Binder. For those of you who have not seen my talk 2 days ago at the Haskell Symposium, let me very briefly explain what HdpH is. It's a parallel Haskell DSL, specifically designed to coordinate parallel symbolic computations. It's for distributed memory platform, and it's implemented entirely in Haskell, just like Cloud Haskell. So you don't do any kind of runtime system hacking to do that serialization. As I said, it's two DSLs, HdpH and HdRS. They do share a common API, so that programs written run theoretically right to the other if they hadn't diverged too much. There's two schedulers for them, work scheduling schedulers. One quality layer that kind of takes into account locality, and the other one for tolerant that should, and does in fact, guard against node status. Now, what I'm going to talk about today, I'm going to give you a very quick overview over the system architecture of HdpH. And then I'm going to spend most of my talk in this tutorial about how we do closure serialization in HdpH, which isn't exactly how Cloud Haskell does it. And we have some different design goals, that's why it is a bit different. Then I'm going to briefly talk about our networking experience and sad stories there. And I'll end, if I have time at all, with a wish list of some things that I think might be cool additions to GHC that would make our life possibly easier. Okay, so architecture. So HdpH is basically a distributed system where you have tasks that sit in a node in a task group, and they can migrate between nodes by work stealing. To get executed, they must be converted to threads. And as threads, they have to stay in the node, can however be stolen by the schedulers, so they can kind of migrate between cores. There's also futures or IVARs that collect results, and they always stay on the node that they were created. And there's data structure, a registry, which is basically translating remote references to these IVARs into global pointers. And there's also, there's a bunch of schedulers on each node, and there's also a message handler that basically deals with that communication. Now, some embarrassing facts about this. Well, first of all, the current data structures aren't really fancy at all. We just basically put functional data structures and put them in an IO ref. And it actually works fairly well because we're doing symbolic computation where the tasks that we actually execute are fairly large granularity. Irregular, but usually rather large, so it doesn't quite matter that we have to go overhead in the runtime system itself. Modularity, well, yeah, I mean, it's all implemented with a deep model transformer stack, and really, it makes it very hard to change. I hate model transformers. It's actually still a small system. I mean, it's really actually embarrassingly small. It's out line of code and about 500 or so just for the closure. So really, I should probably spend more time for sure. Okay, I promise I'm going to talk about the closure implementation, but before I talk about the representation, how it's implemented, let me briefly tell you how it's used. So this would be a small program that you might write in the shared memory palm owner to compute, well, basically something like this. It's summing up this function, which is called the removal function, that kind of does something dependent on how many prime factors one has. It's something that comes from number theory, and it's fairly regular because you have to factorize. So you create a list of tasks here. From 1 to n by applying to this function LB. You then spawn this task, get back a list of futures. Then you basically join the whole list. And in the end, you want to sum up these results. So that's what the program does. Now, if you want to go distributed, this is how it looks. So that's not too bad, I would say. I mean, there's a distance argument here for spawn. Ignore that right now, and otherwise there are a few closures. So the tasks that you're creating, they must be converted into explicit closures so that you can actually use the network. And the same for the results that come back. They also must be converted into closures. Now, that's the difference to closure than is make closure. Make closure basically converts a thunk without evaluating the closure. To closure actually creates closure that forces value inside. So it really is just a serialized value, but it makes a crazy new one. And then because of the closures, then when you get the results, you actually have to map the unclosure function over these results to get the result out of the closure and then do some. So, well, the truth is it's not like that. The truth is actually, because of all the complication that comes largely from not having static in the compiler yet, it's a lot more that we have to do. We can probably ignore this extra thunk that we have to, this typo that that's not too bad. I've also not explained why there is this extra type class to closures where we need instance for. But all this stuff down here is just to do with the fact that when we do these closures, then there will be a bunch of static references in the program flying around. One displayed explicitly, one is coming from the use of full closure here, and this is what the HdpH runtime system itself has. And so you have to concatenate all of these into a static declaration, and later in your main program, at the first instance, you have to really register this stuff and create the static thing. So Haskell has to do the same things, they just call it slightly different. And hopefully, after the second copy day, most of this can go away. Now, let's briefly talk through the API for closures and what in the development of HdpH has been crystallized as the requirements. So the API is fairly similar to what Cloud has. So you have this closure type, which has a factor type argument that says what is actually in the closure. And so one thing that you want to do is elimination, basically take the thunk out of the closure and evaluate it. Of course, the other thing is you want to have an introduction, and so you can only do this in template Haskell. You take some kind of coded expression, you back the coded expression where the type of the second one would be closure A, the type the first one was type A. And then there's also this to closure that converts a value into closure by basically evaluating the value and then serializing and wrapping the closure. Now, requirements, well, one thing is that when Cloud Haskell started, closures were monomorphic. That was lifted sometime later, that they're now rank 1 polymorphic, or not quite fully polymorphic. But immediately when we did HdpH, the monomorphism restriction was a big problem, because what we like to do is not really write a code like that. We like to write a skeleton, a parameter that we can just invoke, and that of course is polymorphic. And so you do need closures that really can have fully polymorphic types. So that's the first requirement. Well, yes, parameter basically. I'll show you. I'll show you in a slide some examples. Yeah. So the next thing is that if you do a closure introduction and then you eliminate it, that should be very cheap. The question is, why would you do that? And again, I'll show you in the next slide. That's what you basically do all the time when you do closures. You create them and then you destroy them again. Cloud Haskell basically creates closures only for tasks that they know that they're going to ship somewhere else. So they always need to be serialized and then deserialized. And so it's never going to be cheap to do the elimination immediately after introduction. But if you ship over the network, then you know that you have to pay this price anyway. So that's fine for them, but not fine for us. And then the third thing is that when you write skeletons, then as you kind of divide up work, you probably want to pack a bunch of closures into larger closures. So when you serialize that, it's important that serialization is still linear in your closures. It doesn't incur extra cost, and the way Cloud Haskell closures are implemented is actually not linear. It's in a similar way as if you do a concatenation of strings and don't use builders, you have a quadratic concatenation suddenly. So, yes, let's get back to some more things.
10 minutes before questions.
Okay, thanks. I'll spend some time here and then I'll go fast. So let's look at what you can do with closures where they need to be involved. Well, one thing is you can write an application operation. You can have function closures like this closure A to B, and you can apply that to a closure A. And the way you do it is very natural. You basically unwrap the closures that we have. You apply the dollar, and then wrap it back in the closure. And well, unfortunately, you can't write it quite as nice because we still don't have static yet. But we can write it like that. So what we have to do is we have to, by hand, abstract the bound variables here. So the argument variables in this expression, and write a top-level function that takes this tuple, and then we can write the expression that normally you would have written in here in the brackets. This is basically, because of the static restriction, this thing here has to be a static function, and currently, without static support from the pilot, it has to be top level. And so we can't really invoke static in here. With the static extension, we hope we can, and then we can really write this thing. So you can also write composition and identity, and it's really just lifting the ID and the top composition through closures in the normal way. And so you basically get the normal properties of function closures as you had for functions. Okay, so I have to go fast here. So I'm fine. Okay. So I'm going to contrast the cloud Haskell closure representation to two closure representations that HdpH has. One that it had until a couple of weeks ago, and one that it has now. So this is cloud Haskell, and the closure is basically an environment that is bound variables in the closure, but already serialized in the byte string, and then this deserializer, which is static. And
so this is a little confusing. You missed out the name of the constructor.
Oh yes,
it's making it hard for us all. So the closure equals base closure or something. Yeah. Otherwise, we'll really don't understand anything else you say.
Yeah, there should be a closure here. So, and this should be the first time. Yeah. Sorry about that. Yes. Yeah. So it's this environment and the static deserializer, and so this is of course serializable, and this thing is serializable because it's static. And this is how you do unclosure. So you basically unpack this static deserializer and then apply. And you see that this then will have to consume the serialized byte string. So if you just before serialize it without sending it over the network, you still have to serialize and deserialize. And this is why the composition is not cheap in Cloud Haskell. Now, as of now, it is rank 1 polymorphic. And the nesting thing it's the same thing about having the serialized byte string already. If you serialize a bunch of things that have byte strings inside them, and you copy byte strings over and over again, you do this one level deep copy, you do this 2 levels deep copy even more, and it's really bad. So this is the HdpH closure representation that we've had for a long time, and it's pretty much the same as Cloud Haskell. Again, I missed out the constructor here. It just had one more argument, this stamp A, which is basically the thing that you constructed the closure for directly plugged in. And so it's a dual representation. You have one representation that you use when you don't serialize, and one, which is these two arguments, that you use if you have to serialize and go over the network. And then, of course, when you deserialize, you have to recreate this one, basically.
I was expecting just to see A then.
Yeah, this stack is some kind of artifact that you needed for the template Haskell to work out nicely. It's to find out when something's partially timed and when something's not. This can probably also go at some point. But it was A at some point, and then we had more complicated code for registering static functions. I can't even remember the details. So the important thing is, if you look at how unclosure now works, it just assumes that this stack is there because it was created by deserialization, or when you create the closure first, and it just pulls out the value. So this is very cheap. And this is why you can do computation with closures in HdpH fairly well. Nesting still not supported here because you still have this problem with the byte string that if you nest the closures then when you serialize, you have to copy the byte strings over and over again. Now this is what HdpH has now, and here we basically have an extremely quantified environment. And I would say that actually this is what Cloud Haskell made to come up with at the time that they didn't quite. So here's a GADT, and it has two arguments: an environment, which is an extremely quantified variable, and then this dictionary, which is again static. And this dictionary just is a collection of the things that you need to do with this closure. And basically, of course, this is basically the abstraction, is the thing that you always have when you deserialize the closure and you validate it. This is for normalizing the environment when you have an instance of NF data. And these two are what you need for serialization and deserialization. These are basically the put and get methods from the respective monads in either binary or data that's serialized. And so when you create a closure, these three fields are actually automatically filled by template Haskell, and it's only the last one that we have to kind of create. And so then the AND closure code is a bit more complicated than before, but it really does the same thing. It applies this ups end to end. First unwraps the static from the dictionary, then takes this abstraction, applies it to the environment, and extracts the function. So this is still cheap, at least as long as unstatic is cheap. And now, because we actually have not serialized this environment, we finally get what we wanted, which was the nesting that is linear. Because now, what happens when you serialize is that the compiler actually constructs out of your puts a builder that builds your line string, and it does so linearly. Okay, I'll skip this just to rant about why we don't like type-rattle. Okay, so a quick summary. The closures that we have in HdpH, they are specifically suited for computing the closures. They're not quite as safe as Cloud Haskell's because we don't ship typeless with the closures. And they certainly benefit from the static extension. And then there's a bunch of things that haven't been covered in the talk, but there's a tutorial in the code if you want to look at that. I should say that because of the template Haskell rewrite, I've actually not managed to compile it to 7.8. Something breaks, and I've not had time to figure out how to fix it. I expect it can be fixed and will be. Okay, very briefly, 2 minutes. Something about networking. When we started it, we basically used an API backend for HdpH, and just handled something that does give here communication of API strings. It wasn't very big, and it worked fairly well for small messages, which is very important for HdpH because the worksheet messages are small and they need to be pumped quickly. But large messages weren't really very good. And what's worse, when Rob wanted to do his fault tolerance stuff, it turned out that there's really no portable fault tolerance for MPI. And on the supercomputer that we tried to run it, we got very spurious crashes in startup before anything happens on the Haskell side, but only once you go to at least 256 nodes. So, I mean, how are you going to debug that? I don't know. So luckily, the network transport library came along, which was developed for Haskell. We use that one. It's pretty much the same way of using it. And it has a very convenient model for fault tolerance, for fault detection, because it basically tells you in the event if a node has failed. So that's great. There are some drawbacks with it, which is that you can't really connect directly to a socket in that library. And so the code is more complicated than it needs to be. And I'm not quite sure about the latency as well. Sometimes we have strange behavior. Okay, I think I'll have to finish here.
Well, if you can quickly
Okay, so some things that we would like. One thing is IO-related priorities, because we have this message handler and it handles messages and needs to do so promptly. So right now we run it on a dedicated core to achieve that. But so we always sacrifice a core for that when most of the time it probably has nothing to do. So IO-related priority, where the message handler will run with high priority and preempt low priority threads as soon as it can compute. That would be something that would probably help us and make the system more reactive. And the other thing that I'm not so sure is a really good idea, if you have large mobile phones, and you quite often have when you're doing distributed computing, because you want to ship large tasks that have large inputs or large outputs, then it's currently the case that you have to create this term in memory and then you have to serialize to byte stream, so you need twice the memory for that, and probably also twice the traversals. So wouldn't it be better if you had some kind of compact representation of mobile phones that you could then directly pump out to the network card when you serialize? That's an idea, and I'm not so sure it will really work because it is difficult to share. And we're going to end here.
About 4 minutes for questions.
What's your mechanism for node discovery?
I use well, either UDP broadcast, or if that doesn't work, I use an MPI or gather that basically broadcasts all to all the endpoints.
So all within the same LAN?
Yes, with the so all within the same MPI program in that case. So the drawback for that is that you actually need MPI still, even if you don't need MPI just for start.
Yeah.
I've seen ML programs do something strange where they just dump their heap to disk and then load it later just to speed up things. Could we use this cloud Haskell and also Geo technology to achieve similar things in Haskell, that you can pre-calculate something and then just don't have to serialize it, but rather dump the heap as it is as a byte stream somewhere?
So I think Nathan Howell can talk about that.
I've been working on trying to get something like that on and off for the last couple of years, but it almost works.
Cool.
And
I have something similar.
Yeah.
we should all talk later about that. And some more questions.
I want you to explain to me afterwards the problems you were having with network, the network transport.
Yes.
Brian?
Did you not see any performance drop in performance when you went from using the InfiniBand network on Hector via the MPI bindings to using the TCP stack?
Well, Hector, we never got the TCP stack to work for some reason. So for Hector, we always used MPI.
Okay. And remind me, what was the reason you rolled your own MPI bindings instead of the pre-existing ones?
Because when we started, there was only one that didn't seem to be maintained, and I only wanted a very small fragment of MPI anyway, and it needed a big library.
And final small bit, has there been a direct comparison yet between GUM S&P and HdpH?
No, there hasn't. There's going to be a multiple challenge where there may be one.
Anyone, some more? I know someone else has questions. Who wants to ask more questions first? Go ahead. Okay, so you're kind of touching on a few interesting points involving trying to reason out the performance characteristics of your network and how it's sort of those sort of not obvious APIs we have, right? Like you were touching on this. The trade-offs of MPI, you didn't have good stability failures. There's a network TCP, you had stronger ordering constraints that you actually need for delivering messages, and that creating sort of non-obvious performance considerations. Is that sort of the right distinction there?
Yes, so I think that TCP isn't really what we need, because we need something that really
reliable but potentially ordered.
Yeah, and small messages really very fast, and you don't really need connections.
I mean, you don't even necessarily need reliability for like a work system, right?
Yes, we could do that. Yes, I think so.
Okay, well, I mean, there's only for a second left. Let's just.
In your new code representation of that little record, the CTIP,
Yes.
you stored a sort of unserialized end and a serialized. Yes, that was in that CTIP. So for the serialized part, you could have just partially applied the serializer to see if you got what hook unit thing or whatever it was. That would be just as composable. Right, it's not clear why you will want to store the separate.
Was the context for nesting or?
It was sort of nesting, so for
Right,
nesting,
so when you have nested things, you use compose fine.
I'm not told that, so.
So, I mean, we were out of time, but it did kind of look like some of the types closure conversions. Have you seen any of the? It really looked like some of the types during closure conversion paper that I read many years ago. I think that's sort of.
I've got some different issues with that. We can talk about that.
Okay, so now we have